Let's take a look at a technique called proof by induction. And we can use this to prove lots of results in mathematics. We're going to look at the first application, which is to series questions. Okay, now if you look at example 1, it says prove by induction. This result that we've already been using, like we know that the sum of the natural numbers from 1 to n can be equivalent to this formula. Now the way proof by induction works is a little bit difficult to get your head around at first, so I want to think of like this analogy instead, okay, and hopefully this will help us to see what's going on with this topic. So I'm going to ask you a question. Imagine you'd like designed a robot and you wanted to know, like, can this robot walk up a flight of stairs? And the answer is, well, yeah, it would be able to walk up the flight of stairs if the following two things were true. So can the robot get onto the first step? And then if it's on one step, could it progress onto the next step? Now, just by knowing these two things, we'd be able to know if the robot could walk up the stairs. Because obviously if it can get onto the first step, it's on the stairs. And then no matter whereabouts it is along the staircase, if when it's on one step, it could also progress onto the next step, then we know that no matter how big the staircase is, the robot would always be able to keep going. Obviously not worrying about like the battery life or anything like that. This is just an analogy, but you know, can it get onto the first step? And then if it's on a random step, could it get onto the next step? And as long as it can do those two things, that's going to allow us to climb this staircase as far up as we want. Which is sort of like what we're doing with these proofs. Like, you'll see what I mean in a second. Okay, so the first thing with proof by induction is we let n equal 1. So this result here, we have to show it works for the first term, okay, for the initial value. I should mention actually as well for this proof, it's saying that we're proving this for n, which is an element of the natural numbers. The natural numbers are 1, 2, 3. Okay, so we're proving this result works from 1 all the way up to whichever value we want. Okay, so we'll start by saying, well, does the result work for the first term? Okay, so what does the first term even look like? The first term would be 1. So would the sum of 1 equal this formula? Does 1 equal 1? Yes. Okay, so what this is basically telling us now is this formula will work for the first term. Like if we wanted to just do the sum from 1 to 1, in other words, the sum of the first term, which is just 1, this sum will add that up for us. So we know it works for the first term. So basically what we know now is the robot can get on the first step. Like the formula that we're trying to prove, we know it works at the beginning at least. Okay. Now we've got to prove that, like, if we're anywhere along this sequence, if we're on the 5th term, if we want to add the next term on, like, this sum will always work. And the way that we do this is we have to assume it's true. For n equals k. So I'm going to state, right, well, the sum of the first k terms is going to equal 1/2 k plus 1. Now, with every proof by induction, when you assume something to be true, we now need to use this assumption. To show it works. For the next term. Okay, so essentially what we're doing now is we're assuming that we're on a step, like we're here, this result does work, with the robot's on the step, but will the robot be able to get onto the next step? Like, So if this formula does work, will it also work for the next term in the sequence? Now the sum of k plus 1 terms, what we're aiming to get to, it's a nice idea to write this down, like we know what the result that we're trying to prove. If this result works for k, we're going to show it also works for the next term, which is k plus 1. So the aim would be the sum of k plus 1 if this result does work, then that would look like 1/2 of k plus 1, k plus 1 plus 1, k plus 2. So that's like our end goal. If we can get to that result, we've proved that it works for the next term as well. Okay. Now this is the next thing we're about to do. We're going to do on every one of these proofs. Okay, so it's sort of like a standard method that you can remember. If we're being asked about the sum of k plus 1 terms, remember we want to use this result here that we're assuming to be true. We need to use this result. So the sum of k plus 1 terms, think about what that represents. The first term plus the second term plus the third term, all the way up to the k plus 1 term. Okay, so that would be, if you think about it, 1 plus 2 plus 3. I'll try and keep it here, all the way up to plus k plus 1. Like, this sum of k plus 1 terms is the sum of all the numbers from 1 to k plus 1. So the key thing that we can spot here is that would be the same as the sum of the first k terms plus the next term in the sequence. Okay, and the next term in the sequence for this question is just k plus 1, because the terms themselves are just the numbers, the natural numbers. Okay, so by realising that the sum of k plus 1 is the sum of k plus the next term, that allows us to use this result. So we could write it as 1/2 k plus 1 plus k plus 1. Okay, remember what I said at the beginning, we want to use this assumption. Okay. So we're aiming to get to this answer here. If we can get to this answer, we've done our proof. We could expand this out, but think about what we were doing with series. I'm going to think about that as 2 halves. Okay, because then I can take out the common factor of a half and the common factor of k plus 1. And instead of having to expand this out and mess about with fractions, I can take a half out and I can take k plus 1 out of both. And if I do that, I've taken a half and the k plus 1, I'll be left with k. I've taken a half, I've taken the k plus 1 out, I'll be left with 2. Which is the result that we were aiming for. Okay, so essentially now what we've done is we know that this result works for the first term. And if we're going to trust that the result works, we can show that it will also work for the next term in the sequence. And just by knowing these two things, if you actually can get your head around the logic, we know that this result will always work. We know it works initially, and we know if it works for one term, it'll work for the next term. So think about the analogy I was saying before, like if it works for the first term, we know the result works. In other words, we know the robot can get onto the first step. And if we're anywhere along, the sum of any terms, doesn't matter what k is, if that result works for k, it also works for k plus 1. In other words, if the robot's on the step, can it progress on to the next step? Well, if it's on the step, it will also work for the next term. In other words, it can also get on to the next step. So we know that, yeah, the robot can walk up the stairs, or yeah, this result will always work for any natural number that we want. Okay. We have to write a little statement at the end. So we'll say, so true for n equals 1, and if assumed true for n equals k. I'm going to write this, which means that implies, so if it's assumed true for n equals k, this implies also true for n equals k plus 1. So by induction, in this case we were thinking about the natural numbers. It might vary, we'll see in some other questions, but we know that this result is true for all n, which is an element of the natural numbers. Okay. I know it's a bit difficult to get your head around the logic on this, but like the good thing is it's a method that we can just learn. Like we'll do a couple more of these and you'll see that the technique is it's very similar, this technique, if we can just remember it. Let's try another one. Okay, example 2, we're going to prove by induction the result for the sum of the square numbers. Just be careful here, we're starting with r equals 0. So our initial step, the first one we're going to check, is we're going to let n equal 0, because that's our first term. So does the first term equal this? Does 0 squared equal 1/6? 0, 1, 1. Yeah, 0 equals 0. Okay, so we know it works for the first term. Now let's assume it's true for n equals k. So we'll trust that the result works. And then we're going to, once we've assumed this to be true, we want to use this assumption to show it would work for the next term in the sequence as well. Okay, so we're aiming to get the sum of k plus 1. Again, it's a nice idea to write the aim, what you're aiming for, so you know. Sum of k plus 1 would be 1/6 k plus 1, k plus 2. Be careful here, if you sub in k plus 1, 2 lots of k plus 1 plus 1, so that would become 2k plus 3. Because you've got, if you do 2 times k plus 1, you get 2k plus 2 plus 1, so that's essentially, you know you've got it right if you get to that form there. Okay. So this is the common theme that happens now. So if you're going to prove the result, you're going to say it's the sum of k plus the k plus 1 term. Okay. So what does that look like? Well, we know the sum of the first k terms is going to look like this. We want to use this assumption. So the sum of the first k terms would be 1/6 k plus 1, 2k plus 1. And then the next term in the sequence, like the k plus 1 term, remember the terms themselves look like this. Like it's 1 squared, 2 squared, 3 squared. So the next term would be k plus 1 squared. Because that's what that term would actually look like, isn't it? Alright, so now that we've set it up like this, we can then look, we're aiming to get to this result. So we want to, just like we've been doing with all the series questions, get a common denominator, look for common factors. So 1/6, think about this one as 6/6. Now what can we take out of both of these? So we can take a 6th out, and we can take a k plus 1 out of both. See what we've got left. We've still got a k left, and a 2k plus 1. Taking a k plus 1 out, so you're left with 6 lots of k plus 1. And then hopefully if we expand this out, we'll get the result that we wanted here. Okay, so a bit of an awkward one to factorise this. 2k and k, all positives. You're looking for 7k. So factors are 6, 1 and 6, or 2 and 3. If we put the 3 there, we'd get 6 plus 2. No, that wouldn't work, would it? So if we put the 3 there and the 2 there, that would give us 4 plus 3, which is 7. But, you know, I could have just cheated and looked here. As long as I was confident in my working, I know I want k plus 2 and 2k plus 3. Okay, just to sort of really justify that we've got this result for k plus 1, you can think about it as k plus 1 plus 1, 2, k plus 1 plus 1. So we've shown that it works for the next term in the sequence. Then write your little statements. I'm not going to write it again because you've seen it in the last one. It's just something that we should remember to write down for that last mark. Okay, I know it's a bit abstract this, but lots of work to follow on this technique. We're going to be looking at induction for lots of different examples. So with practice, it's not actually that bad if you can just learn the technique. Okay, thanks guys.